But before we address these specific structures, we need to talk about the dome as a structural element. And first, we really need to talk about some basic terminology. Now, when we look at internal forces within a dome, we're going to need to be able to refer to their principal directions. And we need some nomenclature to make reference to those directions. A dome looks a lot like half of a globe. So let's borrow some terminology from our colleagues in the geography department. What we want to do is superimpose a grid of latitude and longitude lines over a hemispherical dome. And just as the geographers do, we'll use the term meridian in reference to a line of longitude and parallel in reference to a line of latitude. Now we're ready to talk about how a dome actually works as a structural element. Here we have a model of a dome, and I'm going to use this model to demonstrate how very different the behavior of a dome is with respect to those two principal directions. The direction of the meridians, which we'll call meridional, and the direction of the parallels, which we'll call the parallel direction. And again, the behavior is quite different in those two directions. The meridional direction is quite easy. In fact, in that direction, a dome behaves essentially like an arch. When it's subjected to its primary loading, that is the self-weight of the dome tends to flatten out, and those meridional slices behave just like arches in that they flatten and they extend outward on the ends. They undergo lateral thrust in exactly the same way that arches undergo lateral thrust. So you can expect that containing that lateral thrust is going to be an important consideration in the analysis and design of domes. That's the meridional direction. But now in the parallel direction, we have a very different type of behavior. When I apply that same loading and those meridional slices flatten and spread out, notice that the gaps between the slices get considerably wider. They expand. In my model, that happens because the slices are physically separated from each other. But in an actual dome, that behavior would correspond to tension in the parallel direction. That is, tension around the circumference of the dome. That tension has a name. We call it hoop stress. It's a reference to the iron hoops that are used to hold a wooden barrel together. And it's really a wonderful term because it so beautifully describes the physical phenomenon of hoop stress. Like hoop stress, like a hoop of a barrel, hoop stress in a dome can actually be a very good thing, in that it allows the dome to carry load without any external lateral support. This is the fundamental difference between domes and arches. Unlike an arch, a dome can carry load as a self-contained structural element, but it can only carry load without lateral support if it's able to resist that hoop stress. And since the hoop stress is tensile, that means that the material that the dome is made of has to be capable of carrying load in tension. So that's the good news. Hoop stress is helpful if the domes are made of the right material. The bad news is that ancient Byzantine and Renaissance era domes were all made of materials with little or no tensile strength. The Pantheon's made of concrete. The domes of Hagia Sophia and Santa Maria del Fiore are made of brick. Now, when a dome is made of a material with limited tensile strength, we really can't rely on hoop stress to keep it stable. So the dome has to have substantial external lateral support coming in from all directions, as you see in this graphic. Let's see if we can't replicate this graphic on my physical model by adding that same sort of all-around lateral support to our dome. And to do that, I'm going to use a device called a tension ring, which we'll place over the top of the dome, and which has the effect of containing the base of the dome against that tendency to flatten out, the result of lateral thrust under a load. You might think that this now solves our problem. It'll prevent the dome from expanding laterally. But it really doesn't solve the problem, because when I apply loading to the dome, you'll notice that the base no longer expands outward, but gaps still open up between the meridional slices. So what that tells us is that the tension ring has largely solved the problem of hoop stress at the base of the dome, but it hasn't solved the problem higher up, where we continue to see significant hoop stress occurring at about 1/3 of the height of the dome. Resisting hoop stress is a significant challenge in any dome that's made of a material that has little or no tensile strength like concrete or brick. And the designers of today's great structures met that challenge in a fundamentally different way in each of the three cases we'll be looking at.